verify. Awesome. Hey, welcome everyone. Thanks for coming today. Thanks for coming on our Design Safe webinar series. This is the second one we've had this month. Our last couple have been more involved with more tutorials on using Design Safe and actually doing scientific coding and design and using Design Safe as an actual tool for your science. Previous ones, and sometimes in the near future, we'll go back to some of the cool research that some researchers have done using Design Safe, but we figured this would be a nice kind of break to show you what you can use Design Safe for and how you can use Design Safe for your own research. So my name is Charlie Day. I'm the director here at of Training and Professional Development at the Tax Advanced Computing Center. I'm also the training lead for Design Safe, and it's a pleasure to be with you all today. If you haven't had a chance yet, check out our Design Safe news stories on the front page of Design Safe. One big thing that we would like to kind of boast a little bit about now is Design Safe, our data depot at repository has now become certified data repository by the Core Trust Seal. This is not a simple achievement. This is a huge deal, and we're hoping that we can now give you more secure way of storing your data on Design Safe. So we really appreciate your all's feedback. So this is a QR code that takes you to survey. This should be on the survey now. I don't think it was here earlier today, but I believe it just got added. We'd love to hear your feedback on how you are enjoying these Design Safe webinars that we're giving to you, what you think about the content, what you think about the instructors, and what you think about the pace, and give us some input on what you'd like to see in the future. And we really appreciate your all's feedback so we can give you better content and more focused content on your interests. So with that, it is my pleasure to introduce Krishna Kumar and Scott Brandenburg. Krishna Kumar is a professor here in civil engineering. I've actually had the pleasure of working with Krishna and Scott. Krishna is a professor here in civil engineering. His background is for his PhD was from University of Cambridge on scale multi-phase modeling of granular flows. And he's been developing an exascale micro and macro scale numerical methods in material point method, the lattice Boltzmann and discrete element coupling, and finite elements method, and lattice element method as well. One thing that Krishna has become I would like to say an expert at is machine learning and AI learning, and he's been using Design Safe for a lot of that. And he is an incredibly awesome professor, so it's really great to have him here today. Also, Scott Brandenburg. Scott Brandenburg is a professor at the Department of Civil Engineering at UCLA, where he got his PhD from UC Davis on behavior of pile foundations exposed to liquefaction, induced lateral spreading, and was supervised by Ross Bollinger and Bruce Cutter. Scott is also a co-PI on Design Safe, so it's great to have the PIs of this project give the webinars. It always gives you a little bit of insight on what went into this project, what's going on in this project, and the expertise levels that the PIs have brought to this project. So with that, they are going to be, oops, here we go. So today we are talking about accelerating Python with Cython, Numba, and JAX, which is very cool because I've not experienced any of these. Python is an incredibly popular programming language, as you all know, which is why you're all here. It is not just a language for the DevOps guys or for web development or for data analysis or for scientific programmers. It is a programming language for everybody to use. Why? Because Python is great at collecting stuff and doesn't make a difference what that stuff is. And so everybody has stuff that needs to be collected, and so Design Safe is perfect for that. So today they're going to demonstrate how to vectorize calculations using Numpy arrays, which are significantly faster than the same operations coded in strict Python. They're also going to demonstrate the use of Cython to compile Python code to C, which also improves your performance, and then demonstrate how to use the just-in-time compiler and JAX, which is, as they said on here on the abstract, is Numpy on steroids to accelerate Python, especially when it comes to using GPUs. So with that, I am going to go ahead and hand the floor over to Scott and Krishna. Thank you so much, both of you, for putting this together for us. Looking forward to it.
Yeah, thanks a lot, Charlie.
All right, with that, let me stop my share and hand it over to you all.
All right. I think I'll start my share, Krishna, and I will go back and forth here. So first, Krishna and I have created this little book that goes along with the webinar today. And here I'll put, oh, thanks, Krishna. Krishna put in the chat a link to the book, which is freely available on GitHub. And it also, if you go to the part like on vectorization and JAX, you'll see little links, open and design safe or open and collab, which will open up the notebooks that we'll be working with today. They're partially completed. We do have fully completed versions also here in GitHub, but we figure we might as well, since this is a webinar, go through it together and write the code and talk about the motivation for doing certain things. So I have to say, I feel a little bit of imposter syndrome. I'm a civil engineer, not a computer scientist. And there are a couple of reasons why I thought this was an important webinar. So one reason was that I was just, when Design Safe started, I had never coded in Python or anything. So about 7 or 8 years ago, I started doing this. And I started hearing from people, wow, Python's really slow. Like, it's convenient and these Jupyter notebooks are great, but it's just slow. And then I had a finite difference code that I wanted to deploy as a Python package. It's available as a web, it's written in JavaScript and available through a website. And I thought, I'm going to write it in Python and then deploy it through PyPI, where people can pip install it and run it on their computer. And the calculation that took less than a second to run on my web page was taking a minute to run in Python. And I thought, oh, wow, maybe Python really is slow. Like, there's something to this. And so that's when I started figuring out how to make it run faster. And there are some very basic things that I've learned along the way. I think Krishna understands these things much better than me, so he may have to answer all of the hard questions when you ask them. So I'll get it started a little bit just by talking about some basics of compiled languages versus interpreted languages, and then also just-in-time compilation. So one of the main reasons why Python is slower than a lot of other languages is that it's interpreted, which means it uses an interpreter instead of a compiler. So here's a little diagram that shows what a compiled language does. So this would be like C, C++, Fortran. So you write your source code here, and then you have to push a compile button, and the compiler will read all of your source code, take some time to figure out what to do with it, and then it writes the machine code, which is the binary executable file that will run on whatever hardware architecture you compiled it for. And then you run the executable file, and that gives you your hello world or whatever your first computer program is, right? Print to the screen, whatever it's going to be. Okay, that's a little different from an interpreted language. So interpreted languages use an interpreter instead of a compiler. So you write your source code. Then when you push run, like in Python, for example, so Python, JavaScript, and Ruby are interpreted languages, the interpreter reads your code line by line and decides what to do kind of on the fly. And then it will build some sort of machine code that executes and presents your results. So in both cases, interpreters and compilers are producing machine code from your source code and running. It's just in the way that they do that, it's a little bit different. And the interpreter is doing more work at runtime. The compiler pre-compiles your binary file that you can just call. The interpreter has to do the whole thing, on the fly, on command. There are some benefits, right? One of the things I really like about Python is you can just open it up and start typing variable names, and you don't have to declare the type of them or allocate memory for them or do a lot of the things that you would have to do if you were writing code in Fortran or C or C++. So it's very convenient. But that does come at a runtime sort of execution efficiency cost, because the interpreter is doing a lot of things like figuring out whether that's an integer or a double or a string, right, as it's running. Okay, and then that brings us to the next concept, which is something Krishna will demonstrate today too, which is kind of a hybrid between interpreted and compiled, and it's called just-in-time. So what this will do is that you write your source code and then you run and it's interpreted, but the interpreter produces a compiled code that is then available for subsequent runs. So basically, if you use a purely interpreted language, every time you push run, the interpreter does all that work every time. If you use just-in-time compilation, it does all that work the first time, but then if you run those functions again next time, it's got a precompiled binary that will run much faster and more efficiently. And Krishna will jump in if I say anything wrong, I'm sure, right? Or Krishna, feel free if you want to add some things to it too. Okay, so then we have this little table down here of some pros and cons. So compiled languages have much faster execution speed. We'll show you that today. Interpreted languages are slower. Just in time is faster with a star because it's not really maybe faster the first time you run it because the interpreter has to do all that work, but then subsequent runs, you get the benefit of a compiled language. Interpreted languages are better for code development, right? One of the reasons people like Python is that it's so easy to write your code and run it and get results. And so that's a much lower bar to getting the code to work. And for a lot of applications, it's perfectly fine. You don't have to worry about these performance issues. Whereas a compiled language is harder to develop code in. You have to declare variables, allocate memory, do all of the sort of basic computer science stuff that is skipped over in interpreted languages. Compiled languages do have the benefit of having private code. Obviously, nothing we're doing today is private, but if you were in the business of selling software, you wouldn't want to share your source code with everybody. So if you pre-compile a binary, that's what you share, and that's what people can download and run on their own computers. Interpreted code, you have to have the source code because the interpreter reads the source code every time it runs, so there's no way around it. You have to share your code. I guess with JIT, maybe you could get your precompiled binary and release that without releasing the code because it does compile. But in general, you would have to share your code too. Okay, and then portability. Compiled codes are not as portable. So when you compile a particular piece of code, it's specific to the hardware that you're using. That's why if you go to download software, there's a Windows version and a Unix version and a Mac version, right? They're all different because the compiler has to know what kind of code to run that on. Whereas the interpreted language, I can send you my Python code, and regardless of what operating system you're doing, the interpreter will know how to read it and it will run on that. All right, did you have anything to add here, Krishna, or should I move on?
I'm good. Yeah, we'll reiterate some of these as we cover.
As we go. Okay. Yeah. So we'll move on to the part now where we'll talk about how to make these things run a little bit faster. And so if you go to our page on vectorization and JAX, you can click open in Design Safe or in Colab if you want to. I have to hide my meeting controls. I'm actually going to run it locally on my own computer. So some of the performance that you see, we're going to be timing the, looking at the amount of time it takes for things to run. That'll depend on what computer you're using. So maybe your computer will give different run times than mine. That's perfectly fine. In fact, I think that the JAX example will depend heavily on maybe how many processors you have available too, right? In the vectorized. So, some of these things will not be the same for you as they are for me. So what we're going to do first is just show how a loop, like a Python loop, is much slower than the same calculation done using a vectorized operation where you just pass in an entire array to the function. And we'll just do a really simple problem, signal equals sine of 2 pi f times t, right? Just generate a harmonic function. So what I'll do here is define some input variables like dt equals 0.005. So we'll assume 200 hertz, which is a common sampling frequency for earthquake ground motions, for example. And we'll generate a 2 hertz signal. And then number of time steps, I'm going to set this to be a pretty big number, just so it takes it a while to run through the loops, right? So we'll do 1,000,000. And then once we get out of Python looping, we'll actually go up to like 100 million or 10 million or something like that, because the vectorized calculation is fast enough that it won't take forever. And then what we'll do is initialize a time array. So t equals np.linspace. And I'm just going to go from 0 to n times dt using n steps, and I'll run that cell. And it worked. Great. This is the problem with live demos, right? They say never to do live demos, but this is a workshop. So I'll probably make some mistakes as we go. Hopefully I'll be able to figure them out. All right, so let's do a non-vectorized for loop, just using basic Python. So this has kind of a structure to it set up so that we can do, time.time will give you the current time, and then so you can define a start time and end time and look at the difference between those two to time the execution of what we're doing. And then there's code missing. So I'm going to add some code here in the middle for I in range of n, signal to of I equals numpy sine of 2 times numpy pi times f times time of I, right? So this is a traditional Python loop where we're looping over the range. Notice that I've already initialized signal to be an empty numpy array of length n. So this should run, and it should take less than 39 seconds. That was for like 100 million. I didn't want to sit here for 39 seconds during this demo, so I decreased it to a million number of points. So this one took 2.2 seconds. That's not that bad, right? One thing I'll mention in optimizing code is that you can spend hours saving yourself a few seconds, right? So if all we had to do was generate this signal, 2 seconds is not that big a deal. Maybe it would be fine to write it in Python. But let's go to look into vectorization. And Krishna, did you want to talk about this? You added some things.
Yeah, I can talk about it. I just wanted to mention one more thing. Scott, could you scroll a little bit up? How we mentioned like numpy.empty, and creating that empty allocates the amount of memory required to store the signal. And that's an important step, because if you don't do that, it can dynamically increase the memory, but just knowing how much memory you need to use helps the computer know where to store that at a variable. So like little things like that can catch you, or it can help you a lot. So those are the things we need to look out for, like initializing arrays. When do we do for loop? When do we not do a for loop, and things like that. So like you saw, we're going to show examples that run in a few seconds. So it's like our typical professor job, where we'll do the easy examples and we'll give you all the hard work to do as homework problems. Like if you're running a big finite difference problem or finite element, NPM simulations, any of those, you're going to loop through so many times. So having something vectorized usually helps. So what is vectorization? So vectorization is a computer technique where we're going to leverage an approach called SIMD, which is a fancy way to say you're going to repeat the same instruction or same formula on every single data. Like for example, where we were doing the sine 2 pi f times t, we were doing the same calculation. The only difference was the time was changing, or where we were in that span was changing. So a sequential code like what we've done before in the for loop looks like what you see on the left-hand side, where you go through each iteration. Sorry, this is a C++ loop, but it helps us understand what is happening here. Is each time you're doing a single 32-bit operations. This is how computer languages were written originally, but now we have new hardware where we can do multiple operations at the same time on a CPU. This is not threads. This is just the registry, which is used in these compute operations. Threading will make things faster as well, but we're going to do something called vectorization, where we are asking the CPU or GPU registry to do multiple calculations at the same time, because they are equipped to do that now. So instead of doing a single 32-bit operation, so for example, I want to multiply two vectors, element-wise operation, A equals B times C. I can do one operation, and if I have 1,000 elements in the loop, I'm going to do it 1,000 times, right? Naturally, that will take 1,000 units of time. Whereas if we vectorize, and let's say instead of having one unit of compute that does 32-bit operation, we could do 128-bit operations, where instead of doing one 32-bit operation, you're going to do 4 32-bit operations. 32 bits because we are storing floating point numbers, and floating points numbers are generally 32 bits or 64 bits to store. And we can do 4 of these floating point operations on a single chip, on a single registry to do that. And that's what you're seeing here. So instead of doing and each iteration taking each element in the vector B, each element in vector C, multiplying them together, what you're doing is take the first 4 in element B, first 4 in element C, multiply them together and store it in element A. Instead of doing it one at a time, you're doing like in chunks of 4. So naturally, you would expect an approximate speed up of 4 times, right? So instead of doing it 1,000 loops, you're only doing it 250 times. So that helps, but like the figure below is going to show you how it actually gets executed in a computer. So every time you do this kind of calculation, it's like, think of it like a bus, and each time you only put one person in the bus and send them to a different place. You can do that or stuff the entire bus and move them from place A to B. Which one's going to be faster? Obviously, full bus means you can send in all the 60 people. Same way, if we can store all the floating point operations, do multiple floating point operations in one go, then we get a vectorized loop that can run quickly. So that's what this example is showing, is like non-vectorized loop. You're not actually using all the compute registers that are available on your machine to doing it in a vectorized way where you're just filling the bus and then letting people travel as multiple units of compute at the same time. So I think Professor Brandenburg will now show you the example using Numpy vectorization, and then we'll do the same in JAX as well.
Okay, so if we wanted to do that same calculation in Numpy, let's see, what do I need to, I guess I can call this whatever I want, right? Signal 2 equals numpy dot sign 2 times pi times f, and then we just pass t in as a numpy array. So we don't need to loop. Numpy will know that that's an array, and it should handle the loops on the back end instead. And another reason why vectorized calculations are faster is that Numpy is not actually written in Python. So when it runs loops, the interpreter is not deciding what type is this variable every time and doing a lot of work. Numpy is written pre-compiled, mostly in C. It's a mix of different languages, so it's faster. So if we run this now, we don't need the loop, and it ran in 0.01834 seconds, so about 120 times faster, right? Let's see, we can run it again just to see. 2.47, then we do it again. There are time it operations that you can do too. So 197 times, we've got a speed up of about a factor of 200. And then let's see. Oh, and this one is doing the larger domain size, right? So now how many zeros is that? Is that?
I think 100 million.
10, yeah, 100 million, right?
Yeah.
So we can run this, and then on my computer, it took less than a second, right, to do 100 million, whereas it took 2 seconds just to run 1 million using the loop structure. So do you want to take over now, Krishna, and you can run your screen?
I can share screen and then take over.
Okay.
So, okay, let's see. Yeah, you should be able to see this again. I'm going to risk it and do it either on DesignSafe or Colab, but I want to show a GPU demo, so I'm going to use Colab for now. But you can do it on DesignSafe. Follow me until the very end as well. So, so click on it, and it should automatically open either on DesignSafe or Colab, depending on where you go. Let's scroll down all the way to vectorization. And if you look at the vectorization code, which Professor Brandenburg wrote, and compare it to the for loop, which we had before. I don't have the for loop, but it's a lot more easier to read, right? And that's one of the things that it's easy to know what it is doing. And the other benefit, which you will see later on, is we don't really have to change a lot in how we code, and we can run it on different architectures. So I'm going to run it on CPU and GPU, and we can potentially run it on tensor processing units or TPUs as well. But Google will ask for money for that, so we're not going to do that. We'll do just the CPU and GPU version for now. So I'm going to pick this large domain. So like we have 100 million steps, which we are going to do. So let's go ahead. And if that wants you, it's my code, so trust it and run it. And I haven't imported the library, so let's go import NumPy, and we should be able to do this. So it has initialized an array for the time vector going from 0 to n times dt. Let's do this bigger problem. It took a little over or under a second for Professor Brandenburg's computer. Apparently, Google has a slightly slower version, so we get 1.17 seconds. So far, so good. Now we're going to try to do the same thing like the vectorized operation, but we're going to use a library called JAX. The JAX can do a lot of things. So what we're going to do is like a very small aspect of JAX, which is to do using NumPy and be able to run on GPUs. And that's what we want to do. If you're on Design Safe, I would recommend you run this pip install JAX CPU. We will soon have the Jupyter running on GPUs in Design Safe. That will speed up some of your compute. So if you end up using JAX, by summer, I hope, we will be having the GPU Jupyter version, and you can leverage that in running faster codes. Because JAX is a Google product, I'm not going to run the step, but if you do run it, it will install both the CPU and GPU operations. So here, let's run it. But now, how do I write a NumPy code instead of using JAX? Instead of using NumPy, I need to use JAX. So what we do is we're going to do, instead of import NumPy as NP, you're going to say import jax.numpy as JNP. We're using JNP as our convention, that just to say it's a JAX NumPy rather than a traditional NumPy. And that's it. Wherever you find numpy.something, np.array, np.linspace, we're going to replace that with jnp.linspace. And you can also do this. I think you could do that in the original here, where we defined it as a floating point number with 32 bits. If you want more accuracy, you could do a 64-bit floating points. That just means it stores. That just means it stores a lot more zeros at the end. So here we can go and write the signal which we wanted in JAX, right? So that is signal. We're going to say jnp.sign 2 times jnp.pi times the frequency, and this is our time vector. So what we are doing, like I was explaining about the bus example, is take the entire vector of time and do this operation in almost big chunks. So instead of doing each individual element, we're doing it in chunks, and that's why we get this speed up. So let's do this and run this code here. Did I not run this before? Import jax.numpy. Run that. It is initializing the linspace, and then if we run it again, it takes about 0.23 seconds. So it's already slightly faster than the NumPy version you have. So the NumPy on the same example took 1.17 seconds, and now we didn't change anything much. Instead of calling instead of calling NumPy as NP, all we did was change it to jax.numpy, and we automatically got a 4x speed up. That was great. So how do we do a GPU code? And people always say writing GPU means you either need to learn CUDA, or the best, easiest case, use OpenACC and things like that. What if we don't want to do any of those and stick to Python and NumPy? And the best option we have is Ask JAX. write this code. And here's the most difficult part of running it on GPU. Go to runtime and then change runtime type to GPUs. And sorry, we'll do a CPU version first and then do a GPU. So I'm going to run this again just to see my CPU time. So I didn't realize it was already on a GPU instance. So on a CPU instance, it should take 3 seconds, right? Now let's do the same on GPU. Go here to runtime, change runtime type, and pick a GPU accelerator. So if you do that and then run the exact same code, we haven't really done anything here. All we did was change it from CPU machine to a GPU machine, run that code. Oh, this is because I have restarted the kernel when I switched the runtime. So we just need to wait for it to run the first instance. And then there we go. And then when we do the same operation in GPU, you can see that speed up you get on CPU versus GPU. So CPU took 3.5 seconds, whereas GPU took only 0.2 seconds. All you had to do was change the computer you're running on. And that's the ideal case where we don't have to change a lot of our code. All we need to do is change where we run it. And that's one of the big benefits of using these SIMD or vectorized operation. It's that they are portable. Portable means your vectorized code can run on any hardware. And we've shown you a demo where we took the exact same code, ran it on CPUs and GPUs, and you get pretty much identical big speed ups in changing the runtime operation itself. Let's see if I'll be adventurous and see if I can get a free allocation of TPU. Sometimes they give you an actual TPU, sometimes not. And see if that actually speeds things up for us. So no, yeah, they cheated and didn't give us a TPU unit. So you'll be able to get a decent GPU on Colab, but if you wait until the summer, then you're going to get Jupyter for GPU instance or HPC Jupyter, and you can run your own JAX code, but then it's actually compiling it and running it on a GPU system. So even with this option of copying all your data, which is we are actually copying the time step t to the GPU, do the compute, fetch it back, we still see like a 10x speed up. So it's always great to see big performance increase just by throwing nice big hardware on it without us having to do a lot of hard work. So yeah, I hope you were able to run it and let us know if you have any issues as you run this code using JAX. Do you want to pause for a moment to see if I think there are some questions.
Yeah, Buka asks, can you use your local GPU, or do you have to be on a platform like Colab or eventually DesignSafe's HPC Jupyter?
We could do local GPUs. Just make sure you install. So when you do install JAX, you want to do JAX GPU to install the GPU version of JAX locally. Otherwise, it will only install the CPU version by default. So make sure you're installing JAX, which would require CUDA libraries to be compiled. So pip install should do that, and make sure CUDA libraries are enabled so you can leverage those. So yes, you can run it, but we have a big supercomputer tag, so use that.
Hey, Krishna, why was JAX CPU run slower than just the native NumPy? It wasn't like that when I tried it on my own computer.
Yeah, I think the version, it sometimes is slower because NumPy is specifically tuned for CPU versions, whereas JAX is written to run on GPUs, which means like on a more computing side, the way we store arrays matter. And like GPUs are very good at like columnar data, CPUs are doing rows, major data. So it's the row versus columnar data structures that changes, means NumPy tend to be faster on CPUs. JAX will be much more faster if you're leveraging GPUs and XLAs, which are Google's hardware accelerations.
Ah, okay.
There are more. Yes, so like the reason why you would use JAX is if you're running it on GPU or other faster hardwares. You can also JIT using GPU. We'll show that using Numba, but you can also do JAX.JIT, which will compile it, in which case their CPU version will also be faster. We're going to show the JIT operation later on, so you will see that. But just pure vectorization, Numpy will be faster, but if you want to run GPUs or special hardwares, JAX will be faster. There are other things JAX do, like it will automatically calculate gradients for you, but I'll show that if there's still time at the end. We'll come back and see why JAX is even more nicer tool, not just as a thing to speed up, but to do differentiation automatically.
I want to see that, so I better hurry up.
So I'll give it back to Professor Brandenburg to continue on Cython.
I think I could just steal the share from you, right? Can you see my screen now?
Mm-hmm.
All right, so I'll move on to this hands-on demo of Cython and Numba, and this will continue from the really nice webinar that Charlie did a couple weeks ago, where he solved a heat flow problem using a finite difference approximation. And just as an introduction to Python, right, how to use NumPy and matplotlib to look at things. And so we'll take that same problem and now apply it using Cython and Numba, and also a native convolve operator from SciPy, which is basically a vectorized operator. So okay, so here's the issue. Vectorized operations are very nice when you can do something like pass the time array into a sine function and NumPy knows what to do with it. Not everything that we do is so simple that you can write it out as a single equation where you can pass an array and the package will know what to do with it on the back end. Sometimes you just need to write your own more complicated code. And we do that a lot in Python, but it can be very slow. So Cython is a way of taking your Python code, modifying it just a little bit. You do have to do some extra things to really unlock the potential of Cython, but then it will compile it to C for you. And so you'll have a nice precompiled C function that's efficient and fast, and it will run quickly. And then we'll also demonstrate Numba and JIT and the SciPy convolution operator. So for the heat flow problem, here's some of the background that Charlie covered. If you were at his webinar, this should be familiar. I'll go through it kind of quickly here, but here's the governing differential equation that we're solving. This is the change in temperature with time, and it's 2D, so just X and Y coordinates. And then alpha is the thermal diffusivity. And so we'll do this finite difference approximation here. And we're going to do explicit integration. You could do this implicit too by replacing all these j's by j+1, but you'd have to then do a system of equations. So explicit is easier to demonstrate, probably runs slower than an implicit algorithm. So here's the resulting equation. And if we restrict ourselves to delta x equals delta y, so we just have a uniform grid, then we can make that substitution and the equation gets simpler. And solving for the temperature at the k+1 time step, I guess I and j are spatial coordinate index counters for the x and y dimension, and then k is our time coordinate. So it's explicit because all of our previous times are what are being used to update our evaluation of the current temperature. So this gamma parameter is alpha delta t over dx squared. That's basically a numerical stability parameter. It has to be less than 0.5. Gamma has to be less than, I guess 0.25 for this particular problem. Otherwise, you would get this 1 minus 4 gamma term being negative, and it would diverge and have, really like hugely wrong outputs. So this is the code that Charlie helped us with. We have the length is 50. That's basically going to be the number of elements, so 50 is the length and 50 is the number of nodes in the X direction. Then we'll do 1,000 time steps. We'll make it square. So, it's X and the length in the X and Y directions are the same. dx is just the length divided by the number of elements in the X direction. And then here's dt based on that numerical stability parameter to provide us, we're right on the edge of stability since we're using the 0.25 operator there. And then here's our gamma that we can calculate, right? So then what we'll do is set the temperature along the top edge to be 100 and the temperature along all of the other edges to be 0. And we'll have the plate initially fully at 0, right? So we're just introducing a heat source at the top that will raise the temperature to 100 immediately right at the top. And so this is a transient problem where we'll solve the heat flow as we go. So this is exactly the way Charlie initialized it. We initialize a full array of all the temperatures. So it's got the number of time steps, then the number of X intervals, which is the same as the number of Y. And we initialize it all to the initial, and we're using a float type here. So if I run that, we're good, we're all initialized. And then here's the calculate code using Python loops. So here we're doing 3 loops, right? We're going over all of the time steps in the first loop, and then over the X and Y coordinates in the I and J loops. And by setting delta T equal to basically dx squared over 4 divided by alpha, when we plug that in here, this whole term goes away. So basically I'm only handling this part of the equation because we've selected delta T to be, or we've selected gamma to be a quarter, which means that one cancels out. So it's a little bit simplified here. But anyway, we can define that function, and I'm calling it calculate Python so that we can keep track of, what's going on there. Well, I guess what I haven't done is actually implemented it. So let's do that real quick. I'll insert a cell and we can do T Python equals calculate Python of T comma gamma. And I guess we need our time. I didn't import time yet, so let's do that here. Whoops. So I'll do the Python start time and then a Python end time variable. And then we can do print Python execution time. I'll do this little formatted string thing in here. And then Python end time minus Python start time. And we run it, and this should be about like what Charlie got when he ran it before. It takes about 4 seconds, right? Not too bad. It's not a very big problem. But you can imagine if we use more than 50 elements, our delta T would have to then become much smaller for numerical stability, and the calculation time could really increase. So what we'll do next is implement it using Cython. And so Cython is a static compiler for the Python programming language, which extends it to C. And you can go to cython.org to learn all about it. You do need a C compiler. So if you're trying to run this code, on your own computer, it might not work. If you're running it on DesignSafe, it should work. I assume it would work in Colab also. I'm sure they have a C compiler there. You need the Cython package. So there's a pip install Cython here. And then you also need Python, of course. Okay, there's different ways to do this. So the most basic way is that you write a Cython file, and those by default will have a .pyx extension. And then you write a separate setup.py file that tells Python basically how to compile that pyx code, and it will compile it to C. And so you'll get a .c file that actually has the C source code that was compiled from your pyx file. What we'll do here, which is a good way of kind of getting introduction to Cython, is to use the Cython magic. So if you just type %% Cython at the top of your cell, you've turned that cell into a Cython cell, And all the compilation to C will happen behind the scenes. You don't even know it happened, right? But it will happen. The other thing that we'll do is if you do %% Cython -A, what it will do is give you a little bit of, a window will pop up and show you all of the native Python that's still embedded in your code. And one of the tricks of making Cython really work well is that you want to remove as much of the native Python from it as possible. Otherwise, the compiler will just embed all of the interpreter activities into the source code, and it will do all of the type checking and everything when you run through your loops. So I'll demonstrate that too. Just using Cython and not changing your Python code doesn't actually really make it faster. So here's the pip install and then the load. You have to run this %load_ext Cython to get it to load. So I'll run those. It's already installed on my computer. So requirement already satisfied. If you don't have it installed, you should see a bunch more stuff happening there. And it may take a little while for it to install. And then here's the Cython magic up at the top. So if I run this, right, as soon as you run one of these cells with the %% Cython, it will compile that cell. So these cells usually take a little bit longer to run because the compiler is doing a lot of work. I don't even have any code here, just some imports, right? So let's come up here and grab this function. Whoops. Did a right click instead of a left click. And we'll just copy and paste this function and call it now calculate Cython instead. Right? And we've got T and gamma and everything is exactly the same. So if I compile it, this will work. It will compile for us and give us a Cython version of our code, and we can then test out the runtime. I guess I don't need to re-import time. Get rid of that. And we can change this to Cython. And Cython end time, and then we can do this. And it would be really nice if this would give us a huge performance improvement. It didn't really, right? I mean, it did make it faster. So instead of 4 seconds, it's taking 2.5 seconds. So let's figure out if there are things we can do to make it go faster. What I'm going to do is come up here and type that -A on the top. And now if I run this, it will compile and give me a little window that shows some hints. So yellow highlighting indicates a Python interaction. That means that you probably can make things faster where things are yellow. Now, if you have yellow highlighting outside of a loop, that's maybe not a big deal because the interpreter only has to operate one time and it's not going to significantly slow things down. Here on line 11, my whole line where I'm inside 3 loops is highlighted bright yellow, which means that there's a lot that I can do to fix things. So let's go through some of those things that we can do. Okay, the first thing is that we want to declare variables, right? So inside of our function definition, you can see up here, that function definition is also yellow, and it gives you kind of like some fairly cryptic items here. You can generally figure out what it's saying by reading some of this. It's not very human readable, but anyway, I think this is complaining that we haven't declared T and gamma. So I'm going to declare these as, as arrays. And what I'm doing here is I'm using what's called a typed memory view. So these colons mean that Cython will use this very efficient structure to access NumPy arrays, basically by storing pointers instead of the values themselves. And then gamma is also a double. So if I recompile, I think that that top line will still actually be yellow. Yeah, now it's giving me this little red warning. So this is still yellow. What we want to do here is also define these ones. So we'll use cdef. That's like Cython define as an integer, this nt. So the number of time steps is just the length of the t array. And then we can do cdef int in x, the length of the first element in the c array, which is also the same as, in both directions. Then we're also using some other variables here. We're using k, I, and j. Those are index counters that we should also define. So we'll do cdef int I, j, k. And now if we run this, I think we've probably gotten rid of the vast majority of our Python interactions. Let's see, what is this one saying here? Raise buffer index error. Okay, so one thing the Python interpreter does when it runs is to check whether you've gone beyond the memory allocation of a particular array. Are you trying to access an element of the array that doesn't exist? We know we're not doing that here. So one thing we can do is give it a directive to not do bounds check and not do wraparound. There's also like a check on zero divisions and things like that that you can do in Cython to get it to operate, more efficiently. So, okay, so now I've gotten rid of all of the yellow inside my loops, right? There's still a little bit of yellow up here, which is fine. That's not going to do much. And it's also very light yellow, which means it's not too inefficient. So let's go ahead and run this again. Oh, look at that. Now we've gone to 0.00351 seconds, right? So we've gone from, what was it? 4 seconds to 0.003, right? Let's do a ratio here. We'll do copy this. And I'll put some brackets here. Whoops. This should go outside of that, sorry. Okay, so 1,627 times faster, right? A big improvement in performance by doing what is really not a lot of extra work, right? We had to declare some variables and add this Cython thing and wait a little bit of time for it to compile. So, oh, I see there's some questions in the chat. I haven't been looking at that. Oh, looks like a lot of them are about JAX. So
yeah,
maybe
I've answered them. So yeah.
Okay, great. So I'll stop my share, Krishna, and you can take over for the Numba one.
Mhm. So give people a little bit of time to catch up or check if things are okay, and then.
Was I going too fast? It seems like I was going so slow. It's hard to write code with so many people watching.
I think we already have loaded. Okay, so let's this fine. And let me share screen, and we're gonna do the same operation, but now we'll use the Numba JIT example. I think Cython or JAX are completely different frameworks, so they're not good at playing well together, and you're going to pick one of those three options. So like it depends on how much work you want to do. With like this is my rating, Professor Brandenburg's rating might be slightly different. Numba is probably the most easiest thing to do, unless you have like a really vectorized one, then JAX is easy. JAX does get complicated once you put in classes and things like that, but unless you're developing a library, that's not something I would worry about, and go ahead, use JAX. So mine would be, if you want the best performance out, then Cython. If you have GPU access, but don't want to learn Cython, then just change JAX, Numpy to JAX. But you still don't have time, you only have a CPU, then Numba. But Professor Brandenburg might have a slightly different option. It's a personal preference to, and depends on what problem you're trying to actually solve. So,
and I think you could use them together, right? You could have one cell in a notebook that compiles a function using Cython, and then you could have another cell that's doing JAX, and you could call them both from the same cell potentially, but maybe not. You couldn't.
Yeah, I think like
JAX
my
inside
application is more on writing differentiable code, and I can't actually mix them. So that's why I said it's my view, but it depends on what you want to do.
I agree. I don't think you can mix them in the same calculation too easily. Yeah.
So I'm gonna just run it here so we can do like identical calculations. So we're going to use Numba. JAX also has a JIT option, but Numba JIT is a lot easier for Python libraries already. So we're going to go ahead and let me pull the code which Professor Brandenburg wrote. So this is so we can do some comparisons later on. And I have this already. So that's the Cython code you have. So let's go ahead, compile it, and check what the runtime is in a little bit. Now we're going to use Numba, and we're going to write the exact same function, which is in calculate Python. It's the heat transfer problem. Now we are going to do that using Numba. Numba is basically an acceleration library for numerical stuff, and it does have this decorator, which is just to say at, you're going to do an at about a function name, and that's all you need to do to make it run faster. So make sure you import Numba, and NumPy is already there. We are also going to import numba.type. We're going to import the list, which is a Python list, except we are going to use the numbers list to do this operation. So far, we have not actually changed anything much in the actual code. All we did is copy and paste the Python code for the heat transfer problem. So how do we enable just-in-time compilation? To enable just-in-time compilation, what we are going to do is make sure your Numba library is imported, and you're going to do at Numba dot JIT. And that's all you need to do. And you're going to do this only on top of functions. So make sure you actually have a function. So will be similar for Cython as well. Like you need to accelerate a function rather than a block of code. So I can't put a block of for loop and say, parallelize this for me. It needs to be a function. So that Numba can add a decorator around the function. Decorator is fancy word to say like a wrapper around that function, and then accelerate that function for us. So let's go ahead and
Krishna, real quick, if you had multiple functions in the same cell, you would need that at numba.jit above every single one of those functions.
Every single function, unless you have a nested function, you need at numba.jit on each of those functions. Whichever function you want to compile, you are going to add JIT on top of.
Same thing for the bounds check and wraparound Cython decorators. Those have to go on top of every single function too, right?
Yeah, these are also decorators, right? So anything that starts with an at in Python is a decorator. So it's a nice thing to do with Python, that it's basically a function which wraps around your function. So it's nested function on steroids, kind of. So we're going to do at numba.jit, and let's go ahead and call this so we can run these 2 times, which we have right now. So I'm going to comment out these functions because we haven't implemented them. And let's see the runtime for calculate Python. It should be a few seconds. And Cython was really fast. It took 0.07 seconds. So just to get the benchmark of what we have done before. So if you're doing better than pure Python, we win. Like beating Cython is going to be a lot harder task for us. But let's see if we can beat the 2.7 seconds by just adding at number.jet. So looks good. So we're going to do calculate number. And that's our function we have. So we're going to define the function name. Okay. Instinctively hit save. And then it goes. Okay, I don't need to save this. So we will run it. So this is where it's interpreting the code. It hasn't run it yet. So if I now try to do these operations where we are trying to see how long it takes, but let's just do number and then see if we get the right answer. So after adding at number.jet, we're going to create a new code line and say calculate number. That's the function we have. You're passing T and gamma to it. And let's get the temperature out. So if you run this, that shouldn't have worked, but let's see what the output is, because I'm surprised that worked. It might be different versions of number. We do have temperature. Okay. So this is the live demo problem. Sorry.
Live demos.
Like I was expecting this to fail. I was going to say if it fails with a list issue, then you have to do something else, but like this actually works. So if we try to do a timed run of this, so we have calculate number, I have number time, number second run. So let's call just the number function here. And I haven't implemented the convolution yet, so we'll keep that for later. So if we run this, and you can see that it's calculating, Python took 2.7 seconds, Cython's running at 0.06. Number, there's a first and second run. This is what we meant by just-in-time compilation. The first time you're running number code, it's actually compiling it and keeping it ready for the second run. So ideally, what I would do is like try to pass in a smaller array and a small value. So the compilation time is small, it's ready, it's warmed up, and then pass the big array you want to calculate with. So you may have to call your function twice, but the first time is just going to compile it, and the second time is compile it and run it. The second time it's just running already cached function. So now that you're using the already cached function, you can see that it generates the right heat maps, but it also does it really fast. Yes, we are slower than Cython in terms of 0.006 seconds compared to 0.012. So about 2 times slower than Cython, but we didn't do a whole lot of extra addition. All we did was say at number.jet, and that it was. So I think I know why my error is, because I was trying to show something which I didn't plan, was to do no Python equals true. So this line, by saying this function where we say no Python equals true, basically says, like, here's a Python code. I don't really like to have my Python code, compile it to something else like the C, and then run that, and that will make it even faster. So we are trying to beat this time, which is 0.011 seconds in the second runtime, by saying at no Python equals true. Now, if we try to run this, so hopefully this time it will fail, where I have no Python equals true, and then do it, nope. It might depend on the versions of Python. I guess I tried it on design safe. So let me know if this works. So now we are actually compiling and saying the JIT and saying, don't compile the following function as Python, but instead use a different compile language. So if we go ahead, then run this code, it's still going to take the 2.5 seconds initially to run that, or 4 seconds. Now you're getting closer to Cython times, right? All the difference between running Cython was 0.06. We're slightly slower, but we are actually pretty close to Cython time than the pure Python function. So all you had to do with just-in-time compilation was add the number library and add this number.get no Python equals true in front of your function. That's your function decorator, and that makes your life go so much faster. And in case, so this is in case you have a slightly different version of Numba and Numpy, and it does give an error message that you can't append to a list, then this is how you actually fix it. You can write a simple wrapper. So this wrapper is only in case you run into the problem. So you're going to say T and gamma, same as before. But now we're going to create a list to store the temperature. So T list equals list. And then we are going to append to this list. So we're going to do T list dot append, like you would normally do in a Python code, but you're appending the NumPy as array. And you're going to take the temperature T and append to it. Then we can do the actual calculation, which is T underscore number, call the calculate number function. And you're going to pass the list instead of the, or the first element of the list instead of the original value of T. And then you can return T number. Right. So this is in case you have this problem, but again, that probably depends on the version of Numba. If it complains that the T we pass is not the right type, it should be a list, then you can add a empty list, append the first temperature element to it, and pass that as a list to calculate number function. If it doesn't do this, this is the only thing which we need to do an extra. If it doesn't do it, then you have a good, then you're lucky, then you don't need to do that, and you will have good performance from both Numba in compile time and runtime. So you can see like Cython and Numba giving almost like 0.009 seconds. I'm not going to split hairs in terms of efforts required. And typically, when you are getting a speed up of few thousand times, it's not the Python that's the problem, it's the developer that's the problem. So if we get 5x speed up, 10x speed up, then you can say, oh, JIT did it better, Cython did it better, JAX did it better. If you're writing a code and you got 10,000 times better, you probably need to think about what code you wrote. Or it might not be the right algorithm to do this. So heat transfer problem, it's mainly because Python's interpreted, meaning the way you're using Python for doing a fast calculation is not how it should be used. So let's say, let's go back, look at our for loop. This is the original for loop we wrote, right? We have 3 nested for loops going through the 2 dimensions of space and 1 dimension in time. And you're doing ki plus 1. So row I plus 1th element, I minus 1th element. So 1 at the top, 1 at the bottom, to the right, to the left. And you're doing some sort of convolutional operation. So you're basically taking all of those, adding it together, adding all the temperatures together, and then applying those values, right? So in other words, we are doing a convolution operation, and so you're doing, this is the grid we have. So we'll do the same operation. So this is the grid we have. You're doing, where's the later code? Let me find that. You're doing this operation here where delta x equals delta phi. You have alpha, you have ti plus 1, ti j plus 1 minus 4 times ij, and then you have I minus 1 and j minus 1th element. In other words, if I look at my finite difference grid, and let's say these are my random temperatures, they're all between 1 and 5, so its calculation is easier. I need to do this operation where I need to take I plus 1th element. Ij element is the one in the middle, which is the number 1. I plus 1 is ij plus 1 is the element at the top. J minus 1 is the element at the bottom. I minus 1 is this element 3. I plus 1 is this element 2. So we need to add these 4 values, right? And subtract 4 times the value in the middle. So in order to do that, what we can do is like what we did with the bus example of registry and do 4 operations in one go. We're now going to tell a new operation called convolution, which basically takes a window of matrices and does an operation on that window. And here we're going to take this window and do a particular operation. In this window, we don't actually need the elements in the corners. So we have a value of 0. Convolution is going to do an element-wise multiplication of each of these values. So whatever window we have, the window is the one in the middle, is going to operate on our array. Right? So if I have zeros everywhere, then it will multiply by 0 everywhere, and you won't get any result. If you have ones everywhere, it is just going to add up all the elements and give you the result. So if we want to have a special convolution window, which is like this, so that we can take the first element above us, to the left, to the right, and the bottom, and then subtract 4 times the value in the middle. So that result would be 10. So that's what we are trying to do with our convolution operation. Okay. So how would that look like in code? So let's just, let me see what I have. Let's go ahead, copy this. And this is the same Python loop we have, except for the add_chit function. Now we can define calculate convolution, where we have t and gamma. Now we are going to define the convolution window. So the window in the middle. So that's where we're going to go ahead and define convolution window. In order to define the convolution window, we're going to create a kernel, which is our convolution window. And we're going to do that as a NumPy array. And this is a 2-dimensional NumPy array. So just fill out the rows. The first row is 0, 1, 0. Right? And then the second row is 1, -4, 1. Then the third row is again 0, 1, 0, which basically allows us to define the convolution operation. And we want to ensure that the temperature T is actually a NumPy array. So we're going to do T equal NP as array, take the field and paste it as T. Right, now that we have defined the convolution, we don't need to actually write multiple for loops. We can instead just iterate over time, remove this whole idea of writing 2 different for loops. Instead, we are going to do 1 single convolution. So take that out. Whatever we're going to do in space, we're going to do it purely with convolution windows. So we need to go every k+1 step in time. And we're going to store it in the IJ matrix. And we only want to store it inside. So we actually need to ignore all the boundary conditions. So we don't have to do all of those operations. So here I'm going to do it between 1 to nx minus 1, which basically I2 are 1 to nx minus 1. I don't have INJ. And then I'm going to do also in the y direction, but because this is a square grid, I'm going to do again like 1 to nx minus 1. So I have 1 to nx, and then you have minus 1 to 1, and 1 to nx, and minus 1 to 1. Right. So this allows us to be ready to do convolution. So we've already imported the function convolution or convolve from scipy.signal. So now go ahead and define the function convolve and call the function. We're going to call it over the array, which is the temperature array at time step k. And then we have the kernel, which we are going to use. And you're going to do a mode of the kernel. So how are we going to operate on it? You can just say it's the same kernel mode to operate on. And finally, we need to define the windows on which it is going to operate. So it's going to operate from 1 to nx minus 1 to 1, right? And then 1 to nx minus 1 to 1. And finally, we are going to add the temperature Pk, which is the last term in the temperature field. This again going to go from 1 to 1, comma 1 colon nx minus 1 to 1. All right. So we've defined that, except instead of using a finite difference with 2 for loops in space, we are using a convolution operation, which works very similarly. So we have defined this function. So let's now go ahead and see how much time this is going to take. This is not going to be the fastest of them all, because we are still using like pure Python, but using a slightly different operation like convolution can make heat transfer problem, or you're doing seepage flow and geotechniques, or flow problems, any finite difference windows, you can write it as convolution operations. So let's go ahead. Problem, did I
think you need your gamma
model
in there too.
Oh, that's me doing model instead of mode.
I think the kernel should be multiplied by gamma though, right?
Yeah.
Or the convol.
I am missing gamma multiplication. Yes.
Yeah.
Gamma times convol. So let's try that again. We'll wait painfully the 2.5 seconds for. So you can see that the convolution time is 0.293 seconds, right? It's faster than the pure Python because it's almost Python, except we've used convolution operations, but Cython and Numba are still the fastest implementation. But this was mainly there, like we wanted to show you this so that you can understand there's not just a way to write for loops. There are different operations which you could potentially leverage, like convolution, to make your code run faster. So if we run all this, you can see that they all give you identical results. So it's not just the speed. This is something we should have done at the start, but we know this will work. So we are showing it at the end. That's the first thing we did. It was just like, yeah, we made our code faster, but did we get exactly the same results? And that's the most critical point. Just because your code ran faster, I can reduce the floating points, and that will also give you faster results, but you want to make sure that your code actually produces the correct results in all 4 cases. So we'll just do a quick comparison because of like time. I'm doing a very large scale domain. Let me just do it in Numba directly. So running this, this time we were lucky to beat Cython, but if you do multiple runs, Cython and Numba are going to end up pretty close to each other. So these are some ways you could parallelize, and hopefully you were able to look at different types of parallelization. My recommendation is not to mix all of them unless you're doing a webinar and showing demo of different methods. Pick one depending on what problem you're trying to solve, either convolution to accelerate your problems, JAX if you want to do GPU computings, Numba if you want to do compilation, just-in-time compilation, or use Cython if you want to convert it to a C code and execute it really fast on a CPU-based machine. So it depends on your use case, what approach you want to do, but there are multiple ways we can actually accelerate Python. So see.
Right. I think that's it, right? We can open it up for questions if people have anything to ask. Oh, there is a question about pandas.
Yes,
so use
if you
Numpy and
actually
Cython.
want to do something faster in pandas, there is something called Polar, and that's the faster way to do operations in pandas. So like JAX, there is a faster pandas version. I think it's for Polar, but I don't want to do a live search on.
Yeah, irregardless though, any one of these arrays that you built, we can pull into we can build a data frame from, right? In pandas.
Yeah.
Yeah, that's what I was going to say. I found it to be pretty slow to insert numbers into a pandas data frame, like one cell at a time. It's very slow. But if you create the array using Cython or Numba or whatever you want, then you can create a data frame exactly like Charlie was saying, and use all the pandas functionality on that.
Yeah, some great comments coming through.
Yeah, and Pandas 2.0 or I think it has been released. That uses Apache Arrow backend, so some of those things should get faster as well. And I did promise one other thing on JAX, so let me see if I can do that live. So
Krishna, real quick too, Sergio said that he'd like to see the convolution on the large domain too. Is that going
sure.
to take? I don't know how long that's going to take.
I don't know how long it's going to take, but we can just let it run.
Yeah, we
calculate.
We got about 6 minutes officially, so we got time.
Yeah. All right. So this it's going to take more than 0.5 seconds, I guess.
See, and now Cython's fast. It's
yeah,
hard
it's
to
9
time
seconds.
these things.
Sorry, this is the convolution. Convolution is like, again, like I said, it's a different way to look at the same algorithm. So wanted to present that way, you're still writing it in a pure Pythonic way. Just because you're writing a for loop doesn't mean you have to stick to a for loop. There are different algorithms. So do go search for other algorithms. Hardware acceleration is not the only way to make things faster.
Yeah.
But still, 8.7 seconds would be much faster than if we did it in the native Python nested loops, right?
Yeah.
That's probably not worth trying with this one. This is,
right.
Let's see, you were doing 50 by 50 before. Now this is 200 by 200 with 4,000 time steps, right? So much.
Yes.
I'm gonna guess that would take like minutes instead.
Yeah, we don't want to. Yeah. But yeah, I want to show why like JAX is the machine learning library in case like it's one of the 3 machine learning libraries: PyTorch, JAX, TensorFlow. I think Google decided to compete between themselves and release JAX and TensorFlow and see which one wins. Probably JAX at this point. In going forward in terms of research, that's where we're going to see more. And I'll tell you why, because most of the machine learning models require you to calculate gradients. And let's do a simple function f of x, which basically returns square of a function. Okay. And let's define x equals 3.0. What is the gradient of this function? So we have a function. So let me do this where I can pull it up. I have function x equals x. It's LaTeX. Switching between Python and LaTeX. We have this function f of x equals x squared. We want to take the derivative of that function, right? If you want to take the derivative, which is f dash of x, we're going to say that's 2x, right? So this is us manually doing it. The other way to do it is like manually do it. We're basically doing symbolic differentiation, right? You can also do numerical differentiation. There's finite difference, central difference, Taylor, all based on Taylor's truncation methods. Another approach is called automatic differentiation, which is what drives most of machine learning or underlying most of machine learning. And this is why like JAX is really useful. So let's say we have to get the gradient of this function. All we need to do to tell JAX is take the gradient of the function f. And that's it. It will numerically do it, but it uses automatic differentiation, which means it's much more faster. So we can go ahead and calculate this, right? So grad of x is going to be my function, which is f gradient. And then I pass in the value of x. So let me go ahead and print out what grad x. We are hoping to see 6. And there we go. It has automatically calculated the gradient of that function. This is really useful. So a pitch is we're writing all the simulators or machine learning models, or even your scientific computing, which requires you to take gradients. And if you think like finite difference doesn't give you a very good gradient, then use jax.grad. You can also take Hessian or keep doing it. If you want to take f double dash of x, which is 2, all you need to do is wrap it around one more time. So this is live demo getting even more dangerous, where I have not tried this. And we are basically taking f double dash of x, which should be 2, and we got it. So it's really easy to use for when you're trying to do a differentiation with Python or within Python. Hey, this is the one I promised. So that's the reason why JAX is around. That's the main reason why people use JAX for machine learning, because it can calculate gradients to backpropagate through your models.
So is this used a lot in gradient descent?
Yeah, this is what happens in gradient descents and all the neural networks.
Yeah. Very cool. Thanks, Krishna.
Very cool. All right. Are there any other questions for Scott or Krishna? Okay. All right. I'm going to go ahead and steal your screen back here.
Oh, sorry.
No, that's all right. And wrap things up here. All right. So first off, that was an incredibly awesome presentation. And the reason we're all here in the first place is because you all are scientists, and the idea is to, instead of having to become a computer scientist to write all your code, stick to Python and get your code to run faster. So yeah, these were great techniques, and I'm really, really impressed. I'm looking forward to actually playing with these myself now. So, all right. So thanks a lot, Scott. Thank you so much, Krishna. If you want to catch this again and see any bits and pieces you missed, we will be publishing this to our Design Safe Learning Center training archive. If you basically just go to Learning Center, there's an archive channel there and everything's posted. It'll probably take a couple days for our web team to go through and cultivate it and clear some stuff out and get it set for putting on the web. So yeah, but if you ever want to watch any of our old ones, you can always go back to their archive and see those all printed out there. Also, your feedback, this presentation may not yet be on the survey, but what you can do is you can just select the webinar we gave about a couple weeks ago, which was the Introduction to Scientific Programming with Python. And because it's just kind of a follow-up to that one, that'd be okay. Hopefully that by the time you all take the survey, this one actually shows up on the survey selection. Really do appreciate everyone's time. Thank you, Krishna. Thank you, Scott. Thanks for the shout out, by the way, to the webinar I did a couple of weeks ago. I appreciate that. And of course, thanks to our PIs on this project. And of course, Natalie, to always get these things organized and puts them together in a record amount of time. If you have any questions for us, feel free to hit us up on Slack. You can also email us at training@designsafe-ci.org or fill out a ticket on the Design Safe system itself. Once again, thanks so much. Do look at our training schedule. We have a couple cool things coming up in March, or I'm sorry, not March, but coming up in May. That might be of interest to y'all. So thanks so much, and we will see you all next time. Appreciate you all's time. Have a great afternoon.
And thanks, Charlie, for developing that original heat flow problem. It's good to keep them similar, right? Continuity through the webinars.
No, actually, that was a lot of fun, honestly. We ought to do this one again. That was great.
Yeah.
All right. Okay, if there's nothing else, we're going to go ahead and end this meeting. Thanks a lot for everybody for joining us today. We'll see you all next time. All right, have a great afternoon.
Everybody.
Thanks, Scott. Thanks, Krishna. See you guys soon.
Thanks, Scott.